Hello everyone. Today I shall teach you inverse trigonometric functions. This is a very important material. We shall break it into three different lectures, and this is part one. We are talking now about the definitions. Then we shall do some practice. As mentioned before, I mentioned this when I was talking about inverse functions. The sine function is not one-to-one with its natural domain on the entire number line. So if you have the sine function, sine x defined on the entire number line, is not one-to-one. It takes one of the same value, like 0 for many originals, when x is 0, pi, 2 pi, plus minus k pi, sine k pi is 0. And you see that many originals, many numbers on the number line go to the same image, 0. We can restrict the domain of this function to make it one-to-one. And restricting the domain, we have to keep in mind that it's good to preserve the important features of the function. We have to preserve, for instance, its range. The range of the sine function is the interval -1, 1. It takes values in this interval. We can preserve the range if we restrict the domain to negative pi over 2 pi over 2. So we shall take a domain to be negative pi over 2 pi over 2. So the graph of the sine over this domain, here briefly, let's say this is negative pi over 2, pi over 2, 0, and here 1 and -1. It starts with -1, at 0 it becomes 0, and then grows to +1. So this is the graph of the sine function. And it takes all the important values between negative and +1. And we can see that this graph satisfies the horizontal line test. If you cut with horizontal lines, they will cut only one place. Also, we can take the derivative. Sine x prime is cosine x. The cosine will be strictly positive when x is strictly between negative pi over 2 and pi over 2. So the function is one-to-one over this interval. I shall write this explicitly. Fx, which is now sine x, is one-to-one on the interval d sine negative pi over 2 pi over 2. So when we define the inverse function, we stay with this interval. So we define inverse function as, we shall also call it arcsine. Arcsine y equals x when y equals sine x. We shall use both notations. Arcsine written this way, and on your calculators and some other places you can see also sine inverse written this way, which is not reciprocal. Let me repeat that. Sine inverse of y, this is not 1 over sine y. This notation stays for inverse function. and the domain of the inverse sine will be the range of the regular sine, the trigonometric sine, which is negative 1, 1. And the range of the inverse sine will be the domain of the sine, negative pi over 2, pi over 2. This is very important to remember. And now I shall write the basic relations. Connecting the sine with its inverse. Let's start with this sine arc sine y equals y. Now I'm using y for the range of the sine, and I shall write arc sine or sine with negative 1 in arbitrary manner. So I'm using now this notation. And this identity is true for y in the domain of the arc sine. And here I'm using this notation because it's shorter, which again I want to repeat. This is the range of the sine, and this is the interval negative 1, 1. So this identity is true only when y is between negative 1 and 1. Another identity will be sine, let's write the arc sine. Another identity will be arc sine sine x equals x for x in the domain of the sine, which is the range of the inverse sine, and this is the interval negative pi over 2, pi over 2. So that's important to remember that this basic identity is true only for x between negative pi over pi over 2. Okay, we continue further. Now we are going to the cosine function. Cosine x is not 1 to 1 on the entire number line. It's also periodical. The graph is actually the shifted graph of the sine. And we have to restrict it. We shall take for domain the interval 0 pi. So we take domain cosine to be the interval 0 pi. And the range of the cosine is again negative 1, 1. Let's look at the graph of the function. Here 0 pi, and we have values changing between 1 and negative 1. The cosine for pi over 2 will be 0, and it goes like that. When x is 0, cosine is 1, then decreases to 0, and then goes to minus 1. Roughly something like this. My graphs are not very perfect because writing with this special pen is not very comfortable. Anyway, you can see that this graph satisfies the horizontal line test. The derivative of the cosine is negative sine, and this is strictly negative over this interval. So the function is 1 to 1. Cosine is everywhere decreasing. So we define inverse cosine of y, which also we call arc cosine y, to be x when y equals cosine x, and only for x in this interval. And here are the basic relations. Arc cosine x equals x when x is between 0 and pi. So this will be the range of the arc cosine. Let's write range inverse cosine is 0 pi, close. Domain, the inverse cosine is -1, 1. And the other basic relation will be cosine arc cosine y equals y when y is between -1 and 1. So this is the situation with the cosine. We choose a restriction between 0 and pi where the function is invertible, and we define the inverse function this way. Moving further, now take the tangent function. Tangent x is not 1-to-1 if you consider it everywhere when it's defined. It will be the number line minus the points where the tangent is infinity, like plus minus pi over 2, plus minus 3 pi over 2. So we exclude these points, and tangent otherwise is defined, but it's not 1-to-1, it's periodical. So we take the tangent on the interval -pi over 2 open. At the end points it becomes infinity. So we take domain of the tangent to be this interval, and the range of the tangent, we know that's the entire number line. Briefly, the graph of the tangent function. Let's say here on the left -pi over 2, here pi over 2 on the right side, this is here 0, and I shall draw two vertical lines here. These will be asymptotes for the tangent. It goes like that, from minus infinity through 0 to plus infinity. Okay, so you can see the tangent over this interval is strictly increasing. The graph undergoes the horizontal line test. The derivative of the tangent, which is secant squared x, that's strictly positive over this interval. So we define inverse tangent y, also with this notation, arc tangent y to be x when y equals tangent x, and x is in this interval between -pi over 2 and pi over 2. That's how we define the inverse tangent, only for such axes. And the basic relations, arc tangent x equals x when x is between -pi over 2 and pi over 2, and tangent arc tangent y equals y when y is over the number line, no restriction here. It's good to repeat again that the domain of the tangent is taken negative pi over 2 pi over 2, which is the range of the inverse tangent. It's very important to know where the inverse tangent takes values. And the range of the tangent is the entire number line, which is the domain of the inverse tangent. The graphs of the inverse sine, cosine, inverse tangent can be drawn using the symmetry with the graph of the regular functions. Symmetry according to the y equals x that bisected the first and the third quadrants. I shall draw just the graph of the arctangent. Please look at the other graphs in the book. There are very good pictures. So for the arctangent is defined over the entire number line, takes values between negative pi over 2 and pi over 2. Let's make two horizontal lines for pi over 2 and negative pi over 2. And arctangent functions goes like that. At 0 it's 0, and these two lines are horizontal asymptotes. Okay, now I want to show you how to find derivatives of these functions. To find the derivatives, we differentiate one of the basic relations. For instance, let's write derivatives. Let's take this, one of the last basic relations. Tangent arctangent y equals y. And we shall differentiate with respect to y. Differentiate both sides. Differentiating the tangent, we use chain rule, of course. And remember, if you have tangent u, where u is a function, the derivative will be u prime secant squared u, which we can write this way, u prime cosine squared u. And then differentiating both sides of this identity, which gives you arc tangent y prime over cosine squared arc tangent y equals 1. So from here we can see that arc tangent y prime, this is cosine squared arc tangent y. Sorry about that. Let's write it well. So the derivative will be cosine squared arctangent y. This is not very convenient to keep it in this form, so it is good to write it in terms of some algebraic function. So we can compute what is cosine squared arctangent y. We can do it this way. Let's call arctangent y alpha, and we can use one of the basic relations in trigonometry. We can write cosine squared alpha plus sine squared alpha is 1, and then dividing by cosine squared, we can write 1 plus tangent squared alpha is 1 over cosine squared alpha, which is secant squared. And if we substitute here alpha with its equal, we can write 1 plus tangent squared arc tangent y equals 1 over cosine squared. This is the derivative arc tangent y prime. And on the left side, tangent of arc tangent y is just y, so 1 plus y squared equals 1 over this derivative. And from here we can write that arc tangent y prime is 1 over 1 plus y squared. So this is the rule how to differentiate arctangent function. And we do likewise with the arcsine, arccosine. We differentiate some of the basic identities, and this will give the result. If you take sine arc sine y equals y and differentiate this identity, we have cosine arc sine y, and then by general arc sine y prime equals 1. And following the same pattern, we can write arc sine y prime is 1 over cosine arc sine y. Again with the basic identity, if you call this alpha, this angle here alpha, cosine squared alpha plus sine squared alpha is 1. Cosine alpha will be square root 1 minus sine squared alpha. So I can put this here, 1 over square root 1 minus sine squared arc sine y. And this is exactly y squared because of the basic identity. And the result is arc sine y prime is 1 over square root 1 minus y squared. Very important formula. Now, this formula, this derivative is used also for solving integrals. From here directly we write integral 1 over square root 1 minus, let's say, x squared if you use variable x. The result will be arc sine x plus c. Remember the derivative of the arctangent. I shall write in terms of x. Arctangent x prime was 1 over, just a second, equals here, in the denominator 1 plus x squared. So we can solve now this integral. 1 over 1 plus x squared dx. This will be arctangent x plus c. Now I shall mention the other two derivatives. By the way, I forgot to introduce the inverse cotangent. Let's do it now. We take cotangent x on domain 0 pi. It's invertible there. And the range of the cotangent is the entire number line. So we define inverse cotangent, inverse cotangent y, which we call arc cotangent y, to be x when y equals cotangent x. And basic relations, arc cotangent x equals x when x is between 0 and pi. Sorry, not strict inequalities. That's important. And cotangent arc cotangent y equals y for every y. Every y. The domain of the inverse cotangent, now using this notation, is the entire number line. The range of the inverse cotangent is the interval 0 pi open. Now, I want to finish writing the derivatives of the arc cosine and arc cotangent without derivation. You see, the method is very simple. So let's just write two more derivatives. If you differentiate arc cosine x, you get negative 1 over root 1 minus x squared. If we differentiate arc cotangent x, you get negative 1 over 1 plus x squared. Very similar to the derivatives of arc sine and arc tangent. Just a difference in the sign. Now, for conclusion, I want to repeat the two integrals that we learned from here, together with these derivatives. So remember this. Integrals which appear very often in practice and are very important. Integral 1 over 1 plus x squared dx. This is arc tangent x plus c. Integral 1 over square root 1 minus x squared dx. This is arc sine x plus c. Now, these integrals we can evaluate in terms of arc cotangent and arc cosine if we want for some special purpose, but usually they're given this way in terms of arctangent and arcsine. Okay, I'm stopping for now. This was part 1 of 3 parts on the inverse trigonometric functions.